Hello AP. 8.4 has to do with bond polarity and electronegativity. In bond polarity, it's such a big topic in AP because you're not going to only just see it in this chapter. It's going to pop back up in chapter 9 and chapter 11, especially with electronegativity. You saw that word pop up in chapter 7. We just did not deal with the true definition until right now. So as you see right here, this is unit 2.1 and it has a lot of objectives for it. So let's look at what it is we're supposed to know by the time that we're done. So explain the relationship between the type of bonding and properties of the elements in that particular bond. Electronegativity values for the representative elements, and remember representative elements, these are the A groups, okay? Remember there's 8 of them. It increases going from left to right and decreases going down. So if you look at what they're trying to tell you, what the trend is, and you know we can't just state what the trend is, it increases left to right, and it decreases down a group, but you know I like to look at it when it increases. And whose trend does that actually look like? Well, I hope it looks familiar from chapter 7, electronegativity, and I'm just going to abbreviate it EN. You know you can't do that on the AP test. EN, and same as ionization energy and also electron affinity. Okay, they all three have the same trend. Okay, be very careful when you're trying to relate the 3 of them because they are completely different. 2 of them have to do with energy. 1 is more of a rating system. Okay, so these trends could be understood qualitatively, which means no math. Okay, sorry, no math. Through the electronic structure of the atoms, through shell models, aka electron configuration, through Coulomb's law, and we just saw Coulomb's law in 8.2. Okay, valence electrons shared between atoms of similar electronegativity constitute a non-polar covalent bond. So this is going to be a big word coming, big definition. For example, bonds between carbon and hydrogen are effectively non-polar. Okay, it's going to mean something, even though carbon is slightly more electronegative than hydrogen. So no matter what, any bond between carbon and hydrogens are considered nonpolar. Valence electrons shared between atoms of unequal distribution of electronegativity constitute as a polar covalent bond. So the atom with a higher electronegativity will develop what's called a partial negative charge. And to draw a partial negative charge looks like almost like the 8 is not closed up, or some people call it like a cursive S. And this is what it's called, a partial negative charge, okay? Relative to the other atom in the bond, and obviously the other one would be a partial positive. So versus, oops, that's weird. Let me go back to that. It doesn't like me writing over there. Versus, so partial negative versus partial positive, okay? So this is what happens when it's an unequal distribution of electrons. In a single bond, greater differences in electronegativity lead to what's called bond dipole. Another key thing that's coming in this. All polar bonds have some ionic characteristic, and the difference between ionic and covalent is not distinct, but rather a continuum. We already know what classifies somebody as ionic and covalent: metal, nonmetal, nonmetal, and nonmetal. Okay? So what happens is when they bond, even if it's a nonmetal and a nonmetal, what they're telling you is that even in polar bonds, you can have some ionic characteristics. So they're trying to tell you that there could be ionic characteristics in it, but it's still a covalent bond that's holding those 2 atoms together. So as we go through this, you'll see what we mean by that, but you have a lot of learning objectives to learn for one section. So let's don't stall, let's get going. And I'm going to give you first some definitions and some info. When you have 2 identical atoms, so such as Cl2, H2, so these diatomics, when they bond together, The electron paired must be shared equally. And why it's equally is because you have the same two elements bonded together. Okay, so what happens is we're going to take the electronegativity values for each one of these and we're going to subtract them. And what's the same number minus the same number? Well, obviously 0. So what happens is when that number is very close to 0, they're shared equally. And when they're shared equally, they have a particular name called a non-polar covalent bond. Okay, so that guy's sitting right there or right there. That's non-polar, because non-polar means shared equally. Covalent means non-metal and non-metal, and they're bonded together. So you got 3 terms right there in just one phrase. So once again, non-polar means shared equally. Covalent means non-metal, non-metal, and they're bonded together. When 2 atoms are opposite sides of the periodic table, as we know, sodium chloride, so opposite sides of the periodic table, this is when you get the ionic characteristics. Is because their electronegativity difference, and remember difference means subtract, okay? The electronegative difference between them is great. Okay, and what I mean by great is I can't really give you a value of what is that borderline, what makes it great and not so great. It's just basically when you subtract the 2 numbers, it's a big difference between the 2 numbers. Like maybe one's 3.0 and the other one's 0.5. That's a huge difference. So they're not close together in values when you subtract them. So somebody like sodium and chlorine, sodium a metal, chlorine non-metal. When you subtract those values, when I show you what they look like, you're going to see it's a great difference between them. So basically, there is very little sharing going on. And there shouldn't be hardly any sharing because remember, we're talking about gaining and losing electrons. We're not talking about sharing the electrons. So what happens is the sodium will lose it, chlorine will gain it. So they will have some type of, sorry, let me make sure I get that. All right, sorry about that. Okay, so back to here. When you have ionic characteristics, electronegativity difference is greater than being close together as in values, then you have what's called like a lose and gain situation. Those would be your ionic bonding. So bond polarity is determined about is it equal sharing or is it unequal sharing. So between these two of electrons, oops, I'm trying to highlight it, equal sharing versus unequal sharing, it depends on who the elements are, okay? So number one, we have, like I said, we have 2 different types. You have nonpolar covalent and you have polar covalent. So what a nonpolar covalent is, as we just said right here, it's when the electrons are being shared equally. So like diatomics are always nonpolar, okay? You can have other elements bonded to another one that still is nonpolar. There's a range, okay? Polar covalent is when the atoms, they have greater attraction for bonding electrons than the other. And basically what happens is the difference in value is so large, okay, that what happens is it's unequal sharing. And there is a cutoff to the value of what makes it greater or not so great. But when it gets even extremely, extremely large, then that's when you get ionic bonding. So you have 3 types of bonds. Okay, so all of these are different types of bonds. You could have a nonpolar, equal sharing of electrons. Polar is unequal sharing of electrons. And then you have when the values are so far apart from each other that you have ionic type of bonds. And this is, as I said, this is when you lose and gain those electrons. Well, how do you determine what values are what? Okay, well, you need what's called electronegativity values. Okay, So these are values, and basically what it's determining is these three. From electronegativities, you have to figure out, is that bond nonpolar, is it polar, or is it ionic? Okay? So electronegativity is defined as the ability of an atom in a molecule to attract electrons. That is a big definition right there, because I do not want you to associate it to something else. It's an ability. It has nothing to do with energy. It has nothing to do with it. Basically what it is, it's a rating system. Okay, and you'll see the information coming in just a second. The greater the atom's electronegativity, the greater the ability to attract electrons. When you have an atom that has a very large electronegativity value, then he wants electrons the most. So the greater the electronegativity, the more it attracts electrons. Okay, and there's one side of the periodic table that really wants electrons. And I'm sure you can figure out which side of the periodic table really wants electrons. Well, you know in chemistry we always have to talk about some trends. The electronegativity of an atom in a molecule is related to the atom's ionization energy. Okay, I know you've heard that before, and electron affinity. It says related, doesn't mean it says the same. If an atom has a very large negative electron affinity and very high ionization energy, they both attract electrons from other atoms and resist having its electrons attracted away. So that means it's very highly electronegative. It has a very high ability to attract electrons. So the more negative the electron affinity, the higher the ionization, and you know ionization numbers, these are all positive values, and the very high ability for that atom to attract electrons. I put this table in the notes on purpose here because it wouldn't have made sense in chapter 7, because I don't want you to think that electronegativity and electron affinity is the same thing. If you look at the definitions, you pretty much see the huge difference between it. Electronegativity, it's an ability to attract it, okay? An ability to attract electrons. Electron affinity is the energy released when an atom gains an electron. It has to do with energy. This is just an ability. One is a mathematical property called quantitative, and the other one is qualitative. Okay? It is measured with joules or volts. Okay? kJ, kilojoules, or capital V is volts. And I'm just going to put that on there because you're going to see that word coming in chapter 20. But this is a measuring system. Okay? It's by a scientist named Linus Pauling. And over here, it's applied to a single atom, and it can be applied to an atom or a molecule. There's some huge differences between the two, but the point is, ladies and gentlemen, one is an ability. The other one is an actual release in energy to gain that electron. And that's how that major difference is. So I put that in there because I wanted you to see there's some big properties, differences between the two. So the scientist responsible for this is a scientist named Linus Pauling, and electronegativity values are based on properties, not just ionization and electron affinity. So Linus Pauling developed a system, okay, it's kind of like a scaling system, of which elements want to, so basically which elements are attracted to electrons the most. And you notice on the periodic table that there's one side that's more attracted than the other, okay? And it's based on what's called a scale. It's an ability. So the scale is based on the ability to attract electrons from other atoms. It has nothing to do with energy, not energy to gain it, because that's electron affinity. So Pauling devised a system on the scale of 0 to 4. So 0 to 4.0. Kind of sounds like GPA, okay? 4.0 is an element that is the most attracted to electrons. The lower the number means that they are the least attracted to electrons. Now, when I show you the trend, I already know you know which side of the periodic table wants electrons the most. I know you know. But why is it that? Okay, so it's a scaling system from 0 to 4.0. Now, which side does what? So it always helps to draw your little periodic table sketches. So electronegativity increases as you move left to right. Now that's got to make sense, ladies and gentlemen. It needs to make sense. Why do the nonmetals want electrons the most? Okay, so here it is. From most metallic to most non-metallic, so metal to nonmetal, the effective nuclear charge is increasing faster than the electron shielding. So the attraction that the atoms have for the valence increases. I know that sounds familiar because that's Z effect. It increases left to right on the periodic table. So as the number of protons increases, here's your essay, and I'm going to take a little side note. These red phrases in here, this is from the worksheet that we did, and I know you don't have them in your notes, but I put them in here so that way we can discuss them. It was on that worksheet for periodic trends worksheet we did in chapter 7. So I know you don't have them in your worksheet, but this is the explaining, these red statements here. So you may want to make sure you get them into your notes, okay? But you have them on that worksheet, but let's transfer them over also. So as the number of protons increases left to right, the attraction of the valence electrons increase, and the attraction for electrons increase. The more protons you have, the more attracted the electrons become to the nucleus, and as you gain an electron, it's even more attracted. So nonmetals versus metals are attracted to electrons the most. And it's got to make sense. They are so close to that octet that they just may need 1 or 2 more electrons compared to a metal that needs like 6 or 7 electrons. It ain't going to happen. So nonmetals, the most attractive. So what about in a group? Well, as you go down the group, it decreases. So you know we're going to look at when it goes up. So in a group, why does the trend do what it does? So as it goes up, they want electrons the most. And I think you know why, because it kind of sounds familiar. There's an increasing number of energy levels and electrons that are further away from the nucleus. And because they are further from the nucleus, they're not held as tight, which means your Z effect is very weak. So this is what we expect because we know ionization energy decreases with increasing atomic number. That's a good trend. That's something that you can mention. And electron affinities do not change very much. So here it is again, the worksheet again. The lower the value of the quantum number, the principal quantum number, it indicates that the outer electrons involved in bonding are close to the nucleus. And because they're close to the nucleus, they have a stronger attraction from the protons in the nucleus to the valence electrons. It is literally almost the same as the trend for ionization and electron affinity. It's just the way that you say it, it matters. It is a difference between them. It's all about that attraction. Who is willing to take in that electron, but you don't need energy to do it. So it's an ability. So same thing on the worksheet, okay? Why are there certain groups that have low numbers versus high values? So what group or family, with an exception to the trend of electronegativity values, why are the values so extremely different? Well, noble gases, you're going to see in just a second, noble gases, they don't even have any electronegativity values. They don't want electrons. They're not trying to get an electron. They already have their full octet energy shells. So attracting an electron you would have to put it in a higher energy level, which is too far away from the nucleus, which makes the attraction weaker. And it's not trying to get weaker, it's trying to stay strong. So that's why the noble gases, there ain't any values for them. It's the group right before them, the halogens. They are the very last numbering system. And I think it's on the next page, you'll see the numbers. Why do metals have very low electronegativities? And remember, think about this thing about energetically favorable. They have a low electronegativity because their nuclear charge is smaller. Remember, nuclear charge is the nucleus charge, okay? So aka the proton's charge. And thus, there is less attraction for a pair of electrons in a bond. Most metals, if you look at the elements going across, most metals, they tend to only have like 1, 2, or 3 electrons. They're never going to get to 8. Very, like, it just ain't going to happen. Most of the time, a metal can like share 2 electrons, or they could share up to 4, like beryllium. And these guys could actually share up to 6. But other than that, unless you get to some of the transition metals, they technically could get to 8. Like somebody like tin. Tin does have 4 valence electrons. So he could get up to 8. But he's one of those very big metals. If you notice where he's down there at the bottom, kind of like near mercury and gold, platinum. So he technically could get to 8. But the majority of metals, this is pretty much it. They're never going to get to 8. So their electronegativity values, they're not trying to attract them. They're trying to give them away. So nonmetals are going to go and kind of grab them up. And why do nonmetals have very high electronegativity values? Well, it's kind of the opposite. Because the higher their electronegativity, because their nuclear charge is so large. They have a very high proton count. And because of that high proton count, they are more attracted to electrons. So they want electrons. You got elements like nitrogen that has 5 valence, and oxygen that has 6, and fluorine that's got 7. They want electrons bad. So their electronegativity numbers are very high. So if you notice the numbering, and it's right here, notice the metal side all over here. Remember, the system goes from 0 to 4.0. Technically, Pauling never gave any elements 0. The closest he ever came was a 0.7. So if you notice over here, these are the lowest electronegativities in this corner. And notice we don't have francium on here because francium's nuclear. He's not interested. And then over here in this corner, fluorine is the most electronegative. He wants electrons the most, okay? And I know we're so used to looking at the noble gases as being the highest ionization and the highest electronegativity or electron affinity, but they're not on here because noble gases don't have any values. They're not trying to attract any electrons, okay? So right here, you have the highest element with the highest electronegativity value, and all the way in this corner, you got the lowest. So that's why the trend increases as you go up and increases as you go across. Now remember, Pauling devised, it's an ability system. It's the atom's ability to attract it. Okay, so he obviously, there were some calculations that went with it. We're not interested in the calculations, just why are they attracted. Also right here, electronegativity values, they don't have units because it's not energy. So it's not joules or kilojoules. Okay, so we don't need to worry about any values like that when it has to do with units. So 0.7 all the way to 4.0. Nonmetals have the highest, metals have the lowest. Okay, and the transitions, they kind of go up, down, and up, down repeatedly. So they have kind of like some exceptions into it. We're not really interested in their exceptions. We're more interested in the A groups. So usually on the periodic table, they will focus on the A groups the most. Okay. Now, do you have to memorize values? No, But do know AP does not give values. So I'm going to make the most helpful hint to you. There are some values that I would definitely know. Definitely know carbons, electronegativity, and nitrogen, and oxygen, and chlorine. Okay? I don't want to forget my homie over here, Mr. Hydrogen. I would definitely know them. And notice, ladies and gentlemen, it's not a lot asking. Look at these four right here. They increase by 0.5. 2.5, 3. 3.5, 4. And all you have to remember is chlorine is a difference of 1. So these guys increase by 0.5, but right here it decreases by a whole. And then after chlorine it just decreases little by little, okay? But there are some very probably populated questions where it usually asks about these elements and then hydrogen too, okay? Other than that, you would have to get some assistance on the AP test, but just know AP does not give values for electronegativities, okay? So when you're doing this, ladies and gentlemen, here is kind of like a sneak peek to your gift coming. In your package coming this week, you have a beautiful colored version of the periodic table, and I made sure that I picked this periodic table because this is the same one I use for organic chemistry. And notice right here, this one, now you have them on your periodic table, okay? And now it helps you when you're doing this chapter, you actually have them there for you, okay? Notice right here, noble gases, they don't got any. Now why does krypton and xenon? Is because we have been, back in, I want to say the 1960s, we were actually able to get xenon to bond with fluorine, and we're able to get krypton to bond with fluorine. And why fluorine? Because fluorine's the most electronegative. He's attracted to electrons the most. We have been known to, so they actually now have a numbering system. And notice 3.0, 2.6, that's pretty high. Those are pretty high values. Other than that, the other nonmetals, or I'm sorry, the other noble gases, they don't have any. So when you get your package coming your way, you will see this and you may use this, okay? And I don't mind if you use it on the test of values, but just note you are not going to have any values on the AP test. So you're going to have to remember some quick little trends, okay? So how do we use this? So electronegativity and bond polarity. We can use the difference in electronegativity between two atoms to gauge the polarity of the bond. So what you do is you take the difference. So you take whoever element X is and whoever Y is, and you look up their values, the electronegativity values, and whatever his number is minus whatever his number is. So what you're doing is you're taking the difference between the values. And when these values come up with a number, whatever that final answer is, it's going to mean something, okay? So let's say I had F2. Well, I hope we're not spending time showing that the same number minus the same number is 0, okay? That is always going to be 0. Please don't show that math because that's called wasting time. So when you have 0, you have basically this bond between those fluorines, and they have lone pairs. We're getting really close to drawing these nonmetals. That means that these electrons right here, there are 2 electrons sitting there, because remember every bond is 2 electrons, and because the value is 0, that means that they're shared equally. And I know you just learned what that's called. That's called nonpolar covalent. So when they're shared equally, called nonpolar covalent. So that bond right there, that line between them, is those 2 electrons. This fluorine doesn't have total control and this fluorine doesn't have total control. They are being shared equal. What if you had somebody like HF? Well, if I look at my values up here, okay, hydrogen is 2.1, fluorine's 4.0. So you see right there those 2 values. Okay, and I usually just put them right above them. So hydrogen's 2.1, 4.0. When I subtract those values, I get 1.9. Now that's a pretty big difference. In chemistry, that's pretty big. So because it's a nonmetal and a nonmetal, what happens is those electrons right there, because of that big difference, they are not shared equally. And what happens is that the element that is the most electronegative, he's pretty much possessing those electrons the most. So first, they're not shared equally. And what happens is those electrons, let me draw the dots. Remember those two electrons between them? They're a little bit more pulled towards the fluorine than the hydrogen. So he is dominating those electrons. They're being shared, but not equally. That's something very key that you understand with this. All molecules share electrons, but the question is it equal? Because if it's not equal, then that's called polar covalent. So those electrons right there, because fluorine is more electronegative than hydrogen, he is dominating those electrons. So what happens is he has a greater electron density around him than the hydrogen. Okay? So you're still going to form a bond, but now the bond is called polar covalent, not nonpolar. And when the difference becomes, as I said, remember, very great difference between it, a giant great difference between it. And I know you're like, but it's just 3. I mean, that's like not even that big. When the highest number is 4, and when you subtract, the answer is 3, that's a pretty big difference. So then you start to notice, who is it? Well, I see lithium. Well, that's a metal. And I see a non-metal. And ding, ding, ding. That's called ionic. So the bond between them, that Li and that F, okay, there's very little sharing happening. What happens is fluorine pretty much has almost like all control, but they did make a bond between them. Okay, so it's not about unequal and equal sharing. It's fluorine's pretty much he took control a long time ago, because remember, this is called lost electrons and gained an electron. So he took that electron away, but they did form a charge. That lithium was still attracted to fluorine, and now you have an ionic bond. So that is the difference between it. That is literally the math that you are doing with this. You are taking the electronegativity values and subtracting them. And what happens is there's a range. So I'm going to put these ranges right here, and you're going to want to like box it, highlight it, whatever it is. When you are finding the electronegativity difference, after you subtract, if it comes anywhere between 0 and 0.4 when you subtract, it's considered a nonpolar covalent bond. So let me give you an example, because every CH bond is always nonpolar. It's always nonpolar. So if you look at the values for carbon, look at our fancy new periodic table. Carbon right there is 2.5. Okay, as you see right there, 2.5. And I got hydrogen over here, 2.1. That's why I said you need to know some values, so you don't have to be looking them up. If carbon is 2.5 and hydrogen's 2.1, when I subtract those two values, I get 0.4. And it's right there on the borderline of the range. So the electronegativity difference, the range to whether it will be polar or nonpolar, that's 0.4, which means every CH bond is always going to be a nonpolar covalent bond. Always, always, always. Okay? What if you have somebody like HF, which HF up here, we already know it's going to be polar. Okay? So we already did the math, 1.9. Here's the problem though. No one can ever determine, or I'm sorry, no one can ever decide on what it goes up to. When I learned it back in the day, it went up to 1.9. However, more and more in AP, I'm seeing that this value, actually they're saying about 1.7. So it could be 1.9 to 1.7 that it goes up to, but the key is this. Look at who the elements are first. If you see a metal, ladies and gentlemen, I mean, you can't even be thinking about this category. I mean, you got to go straight ionic. But if you are doing the math and you get 1.9, and somebody like hydrogen that's a nonmetal, and fluorine that's a nonmetal, you know that cannot be ionic. Not even close. Does it have ionic characteristics? Yes, it does, because the difference is so big. but it's a nonmetal to nonmetal. So because when you subtracted this, as you saw, you got 1.9 in the difference, so 2.1 to 4.0, that difference right there, okay, that means it's a polar covalent bond. Okay, and a polar covalent bond means that the electrons are not shared equally. So what you do is you write these things called charges. Partial positive charges versus partial negative. So these two symbols, partial positive and partial negative, what you're telling me is that in this bond right here, this bond between them, that one, it's not shared equally, but the positive and negative is telling me who's dominating, okay? So what happens is the partial negative is the element that is most electronegative. So if fluorine is 4.0, he is the most electronegative. So he gets the partial negative. We used to call them deltas because of the Greek symbols, but I'm going to call them their name that AP has them now, partial negative. And the least electronegative, which is hydrogen, would have that symbol, little partial positive, on him. So if and only if it is polar, you have to indicate who is partial positive and negative. But only if polar. Okay? Please, I'm going to circle that, box it, whatever, highlight it. But you would never do this if it's nonpolar because it's shared equally. So only if it's polar, you will probably have to indicate, and like I said, it was called a delta plus and delta minus. You would have to tell me who's the most electronegative or not. If you have that metal, okay, and you've already done the math, you know lithium is a metal and fluorine is a nonmetal. There's no point to do the math, ladies and gentlemen, because it is straight ionic. You have metal and nonmetal bonded together. It is not polar, it is not nonpolar, because polar and nonpolar has to be a molecule to begin with. That is a compound. That's an ionic compound. So when you do the difference in it, you saw up here on the math, it was 3.0. That's beyond ionic. So usually what happens in that ionic range, so right here is the nonpolar range. This is the polar range. So then for the ionic is usually anything, and I'm going to put this little approximate, usually anything 1.7 and above. I can't tell you if it's 1.7 or 9 because scientists, they've never agreed on what's the cutoff besides looking at the elements first. So when you look at the elements first, is it a metal and nonmetal, or is it a nonmetal and nonmetal? Okay, because you know if there's a metal, you better be looking at the ionic category. So what happens is with ionic, you get a huge difference in electronegativity between the atoms. There is one atom that is completely dominating those electrons. They have pulled them so close that the other element is barely hanging on. So with those two electrons, when you get that fluorine and lithium, because remember lithium lost that electron and fluorine gained it, one of those electrons, that valence electron, it went straight over to fluorine, and now fluorine has it. But they still created a bond. So between that lithium and that fluorine, they right there are sharing electrons. But fluorine has more possession of them than anything. So lithium's kind of like attached, kind of like along for the ride. He's pretty much doing whatever fluorine says. So that right there is what an ionic bond is. It's that lost and gain attraction between the metal and the nonmetal. Okay? So hopefully you're seeing the distinction between them. This is a very tough topic. So when we draw these, as you see, that's diatomic fluorine. And notice this region right there. Well, that's equal sharing. You have this electron density that's the same size as the electron density over here. And these are called electron electron density diagrams where you actually see the difference in sizes. But notice HF. Remember, HF is that polar covalent. And notice how those two electrons being shared, well, remember, fluorine is possessing them. So you have a greater density for electrons than hydrogen. And that's got to make sense. Hydrogen's the smallest atom on the periodic table. He should not be big. Fluorine has 9 protons and electrons, and now he just gained one from hydrogen. He's huge. And then you got lithium fluoride, which we know that bond is ionic. And fluorine is totally dominating that compound. So the more an atom is attracted to electrons, the greater the difference. But if you have something like this where the difference is small for electronegativity, it's going to be nonpolar. But then you got a large electronegativity difference, and that makes it ionic. So the more they're different from each other, the more it's going to tend to be polar or ionic. So like I said, there's usually a chart right here. I've seen it go to 0.4, and I meant to change this right here, 0 to 0.4, and then anything above 0.4. So usually 0.41. I wasn't able to edit this table that I found on the internet, but AP has always said anything above 0.4 is polar, and above 1.7 is ionic. Just be very careful if it is 1.7. First, look at the elements. Okay, is there even a metal? Because if there's not a metal, then it is not going to be ionic. And look at that, metal, metal, metal. And even right here, you still see no, in this polar category, you do not see any metals. So let's do a little bit of practice with this. Have your periodic table kind of near you, your new fancy periodic table. In each case, which bond is more polar? So boron versus chlorine, okay? Or chlorine versus chlorine. So the first thing is you need some electronegativity values. So right here, we got chlorine as 3.0, and we got boron as 2.0. So just list the values underneath them. So between the two, who's going to be more polar? Well, obviously this one. And why? This is literally it. The electronegativity difference is greater than that Cl2. 3.0 minus 3.0 is 0. So this is what we call a nonpolar covalent bond. And because when you subtract this, it's going to equal 1.0, which category would it fall into? Well, it's going to be polar. So over here, it would be a polar covalent bond. Okay? And letter B, you have P and F, and we already know fluorine is 4.0. And we have P versus Cl. And Cl is one of those that we should know, 3.0. So now we just got to look at phosphorus. Now, you should be able to predict, without even looking, this number minus 4.0 and the same number minus 3.0. Who's going to be the greater difference? I guarantee you it's going to be this first one, because phosphorus is the same in both of them. So phosphorus on here is 2.1. And if I subtract 2.1 minus that, and just so you know, ladies and gentlemen, when you subtract, you always subtract the biggest from the smallest, so you do not get any negative answers, okay? So biggest and smallest, you get 1.9, and that right there is covalent. Could it be in the ionic category? And no, because neither one of those are metals. So see right there, it's kind of like an approximate, even though it says greater than. It just needs to be still nonmetal and nonmetal, and it's still classified as a polar covalent. And I'm going to put right here, not ionic, since they're nonmetals only. So you have to be very careful with that ending range. Phosphorus 2.1 to 3.0, well, you're going to get 0.9. And you're still polar covalent. But which one is more polar? this one. The greater the difference between electronegativity, the more polar. Let's get that down. The greater, I know it's somewhere in my notes, the greater the electronegativity difference, the more polar the bond is. Okay, and actually more specific, the more polar covalent the bond is. Okay, which of the following is most polar? Okay, so if we listed these, okay, so notice you have the same two halogens versus the same two halogen, bromine and bromine. You have sulfur and sulfur, and then selenium and selenium. Sometimes with this, you have to look at the location on the periodic table. So I had sulfur and chlorine. They're literally sitting like right next to each other. I had sulfur and bromine. I had selenium and chlorine. And then I also had selenium and bromide. Well, the elements sitting right next to each other, their difference is so small. But when it's diagonal like this, you get a little bit bigger range. So sulfur's 2.5. Chlorine, we already know, is 3.0. Okay. The bromine, I think it's 2.8. Where'd it go? Yeah, bromine's 2.8. And like I said, you can't use those electronegativity values because you won't get them on the periodic table. So I'm trying to show you some trends here. So selenium, it said selenium was 2.4. So if you write these on the periodic table like the way they are, you got sulfur right here, selenium sitting right below him, and then you got chlorine sitting across sulfur, and then bromine sitting across it. So on the periodic table, this is what it looks like. So what you would have to do is you'd have to actually use the positions of the periodic table where they're at. So notice right here subtracting, you're going to get 0.5, subtracting 0.3, subtracting 0.6, subtracting 0.4. And what did I tell you? When they're straight across from each other, that difference is going to be very low. But if they're diagonal with each other, you actually get a bigger difference. And notice who's the biggest difference? Selenium and chlorine, because he has the greater electronegativity difference. So before you ask me how to explain it, that's how you explain it. The greater the difference in electronegativity, the more polar it is. Okay? So when you are trying to do this without any numbers, okay? So when you have, so if no electronegativity values given, and you know it's not going to be given, look at position on PT. Look at where they're at on the periodic table. Elements that are literally right next to each other, they're going to have a small difference in electronegativity. But elements that are kind of diagonal with each other, they will have a bigger difference. Now, it's not huge. I mean, look, you got a 0.5 and a 0.6, 0.4 and 3. It's not going to be a huge difference, but it will be a bigger difference when they're diagonal with each other. And obviously, if you're looking at somebody that's like 2 boxes away, so somebody here and here, you'll get even a bigger difference. Okay? So it's all about looking at position on the periodic table. So where are those differences? Okay? For each of the following polar bonds, which atom has the partial positive and which one has the partial negative? So look at your periodic table and who is the most electronegative. And I don't even need to put the values up, okay? You got carbon, don't look at the values, carbon and nitrogen. Remember, electronegativity increases as it goes across. Nitrogen is going to be the more electronegative. So because nitrogen is more electronegative, he will have the partial negative charge, and carbon would have the partial positive, which means those two electrons, they are being possessed by nitrogen more. Now this is a no-brainer. I don't even have to look. Fluorine is the most electronegative, so he will get the partial negative, and bromine would be at the partial positive. Okay. Now silicon and oxygen, I know they're kind of close to each other. Silicon and oxygen, you got oxygen right there, and you got silicon like 2 blocks away. Now, remember with electronegativity, it increases as it goes up. Oxygen is definitely, I'm not even looking at the numbers, oxygen is definitely more electronegative. So because oxygen is more electronegative, partial negative, and silicon, partial positive. So same thing, look at position on the periodic table. Could you arrange the following from least polar to most polar? Okay, so they all have fluorine in common, but where are these elements? Okay, I'm not even going to look at values. So on the periodic table, I got fluorine that sits right here. I have oxygen that sits right next to it, and then I got nitrogen that sits right here, and then phosphorus sits right there, right below nitrogen. Now, you already know that the difference between each one of these is a 0.5 difference. So 0.5 and 0.5. So between oxygen and fluorine, because like I told you, you should know some of these trends. Between fluorine and oxygen, you're going to get a 0.5 difference. And between nitrogen and fluorine, 0.5 plus 0.5, you're going to get a 1.0 difference. But look at where phosphorus is. He is a greater distance from that fluorine. So I don't even need to know his number. Okay, I know it's going to be a difference more than 1.0. And if we look at the periodic table, phosphorus 2.1, 4.0. That's huge. That's huge. That's like bordering the ionic characteristic. So all I need to know is that he's just more than 1.0. And I just looked at position. So the least polar would be the smaller electronegativity difference. And that would be OF. So I'm going to put OF right there. And we're going to use our greater and less than signs. And the most polar would be the bigger electronegativity difference. And that would be the PF bond. Okay? And then obviously the nitrogen and fluorine one there. So the point is, ladies and gentlemen, do not rely on this beautiful periodic table to try to figure it out, because on the AP test, you're not going to have numbers. Look at positions. Look at where they're at. So when we do a polar bond, we have a symbol that we use called a dipole. And you saw this word at the very beginning of the video. What a dipole moment indicates are polar bonds. And this is only for polar covalent bonds. In this dipole moment, you are basically telling me who is possessing the electron. So it's kind of like the partial negative and positive. We just have a different symbol for it. So in HF, which we already know HF is polar, so in this polar bond, is because hydrogen is 2.1 and fluorine is 4.0, and we get 1.9. Very, very, very polar. Okay? And remember, there is no negative answers. The concentration of the negative charge on the more electronegative, so you saw this picture right up here, electron density. Very, very, very electron dense in the fluorine region versus the hydrogen. So because of that, you create what's called a dipole moment. So both bonds and the entire molecule, they're not only polar, but they also have a little bit of nonpolar with them too. So beware, you can have polar covalent bonds, but the entire molecule still end up in nonpolar. Now, like I said, this is coming here, but I stated it here because you know it's coming our way. But right now, we're just trying to figure out, is the bond polar or not? Okay? So we only have 2 elements, and that's all we need to figure out is those 2 elements. So because hydrogen is least electronegative, he has the partial positive, and because fluorine is more electronegative, partial negative, we draw what's called a dipole. And what that dipole is indicating, let me make some notes over here, okay? It's an arrow with a little plus sign on the end, because this plus sign is representing the least electronegative, and all these electrons, see these two electrons that are sitting right there in those bonds? Remember, there's two electrons sitting there? The fluorine is taking charge. Those two electrons are literally being pushed up more against fluorine than the hydrogen. Remember, they're still sharing. They are sharing the electrons, but unequal sharing. And that's why it's called a dipole. You're telling me who is possessing those electrons more. So the point is, ladies and gentlemen, is does AP want partial charges? Do they want these symbols instead? Or do they want you to draw what's called a dipole moment? And a dipole moment is telling me who is possessing those electrons. So when two electrical charges of equal magnitude but opposite charge, positive and negative, they create what's called a dipole, aka a dipole moment. In the notation on the right, the arrow denotes the shift in electron density towards the fluorine because he's more electronegative. He wants those electrons the most. The crossed end of the arrow, the little positive part of it, indicates that the positive end of the molecule is least electronegative. So some famous molecules out there, CO2, SO2. So if you actually did this, oxygen is electronegativity 3.5, and this oxygen, same thing, 3.5, and carbon's 2.5. Oxygens are more electronegative. So look at those dipole moments. The dipole moment's going away from the carbon, and this dipole moment's going away from the carbon. So these electrons that are in here, remember there's two electrons in here, and there's two electrons in there. All four of those electrons are being possessed by oxygen more than the carbon. Same thing here. You have this sulfur. I know oxygen is number 3.5. Sulfur is less electronegative. I don't even know what it is. It's like 2.5. Okay, same thing. Huge electronegative difference. And notice both of those dipole moments, they're going away from sulfur. Okay, and we've already done HF. Fluorine, the most electronegative, it is possessing the electrons most. So the point is, the name of the game is it equal or is it not? But if it's not equal, then who is possessing them more? Okay, so you only do a dipole moment if you have a polar bond. So if it's nonpolar, like diatomics, you will not have any dipole moments because it's not polar. It's got to be polar to have a dipole moment. Okay? Polarity helps determine many properties we observe at the microscopic level. So polar molecules align themselves with respect to one another, and the negative end of one molecule and the positive another, they start to attract each other. So see right here, you have positive and negative. And this negative is attracted to this end of the positive and negative, and then attracted to this positive and negative, and so forth, so forth. So polar molecules are likewise attracted to ions, okay, ions, positive and negative. The negative end of the polar molecule is attracted to the ions. And you saw this in chapter 4 when we drew water. And we had these ions floating around in water. And what part was attracted to what? Well, water is very polar. And I'm going to put that right here so that way you will never forget that. Water is a polar molecule. And this positive right here is attracted to the oxygen that's negative, and the negative is attracted to the positive part on the water. It's the whole thing you've been seeing since chapter 4. Okay? You will learn a special name called ion dipole in chapter 11. That's why we need to be very good at electronegativities. So this picture right here, you also see how size makes a difference in polarity also. The change in electronegativity difference has a greater effect on the dipole moment than does the change in bond length. So remember with size, okay? When it comes to size and electronegativity. So with electronegativity, nonmetals want electrons the most. But what about radius? Well, radius is the opposite trend. Atomic radius. So notice right here, fluorine is a smaller atom. And you got iodine, that's a bigger atom. So just notice its electron density, okay? Is one more polar than the other? Yes, okay? This one definitely right here is going to be more polar, okay? Because fluorine is most electronegative. And you got iodine, that is least polar, but it's a bigger molecule. So you're seeing some trends here. The more polar it is, the smaller the atom. Okay, and actually I should probably say the word ion, not really atom, because fluorine is bonded. So I'm going to change that. The smaller the ion, aka fluorine. Fluorine negative. But the bigger the ion, aka iodine, iodide, the least polar it is. Okay, so there are some trends right there. Has to do with size and electronegativity. Bond types and nomenclature. Nomenclature is a fancy way in chemistry on how to name compounds. Be very cautious when it comes to the metalloids, okay? And be very cautious when it comes to transition metals. Usually there are two types to name binary compounds. Remember, binary means two elements only. One is for ionic and one is for molecular, which we use prefixes, okay? In both systems, the less electronegative is given first, and the other one, the nonmetal, has the ending IDE. So anytime it's been nonmetal and metal for ionic, the least electronegative is the metal, and the more electronegative is the nonmetal. And then we just change that ending to IDE. Same thing with nonmetal and nonmetal. The first one is still the least electronegative. Both approaches are sometimes used for the same substance. And what you will see is sometimes the transition metals, they like to sometimes be named, sometimes, like molecular. For example, TiO2. Now we know that is straight ionic. Okay. However, we actually have this chemical in the stock room, and his name on the bottle actually looks like this, titanium dioxide. And when you're looking at that, you're like, wait a minute, they just named it with a prefix? They just named it like it's a molecular compound. And that's okay. If they name it that way, they name it that way. They're trying to help you with the biggest hint ever. You have one titanium and two oxygens. However, this is the proper naming because it's ionic. Okay, so this is the preferred naming because it's ionic. However, if you see it like this on the AP test, don't freak out. Don't tell Mr. AP, hello, on the AP test, you made an error. Okay, no, they're just naming it that way. So you will see sometimes transitions, and you will see metalloids do this too. Okay, so sometimes metalloids, when they bond with nonmetals, they sometimes like to be named like a molecular compound. So don't freak out. It's not an error. It's just sometimes it happens. Doc Dina has a little quick video to help you with polarity, and she looks at these three right here. So I put it on your teams, and you'll notice it's right there. Okay, so 8.4. In her video, she's going to do some examples with you that are also in the notes. So right here, after you watch